Hello, everyone. This is a problem from the 1994 AIME. This was a problem 13. Let me show you how to solve it. So we're given 10 complex roots satisfying a given equation, and we want the value of some sum involving all of them. So let's just start off by rewriting what we're given. So we have x to the 10 equals negative 13 x minus 1 to the 10. So this shows us that x and 13x minus 1 have equal magnitudes on the complex plane, but x to the 10 and 13x minus 1 to the 10 will have opposite angles on the complex plane. Therefore, we can actually interpret this as 13x minus 1 being a rotation of x around the origin, where our rotation factor is some 10th root of negative 1. Keep this in mind. It's going to become important in a couple of steps. This easily rewrites as 1 over 13 minus theta. So this looks a bit like annoying that we have this stuff in the denominator and like it's just a weird fraction, right? So you look back quickly. The value we're being asked to find are actually the reciprocals of the solution times each other. So we can actually just consider the reciprocal of the solution here, which is of the form 13 minus theta, which is a lot easier to look at. And let's actually expand theta out here. So yeah, 2k plus 1 times pi over 10. And now this is not an even multiple of pi in the numerator as you usually see, because we're not looking at roots of unity per se, but we're looking at 10th roots of negative 1, so we want an odd multiple of pi in the numerator. And now we're really close actually to what we want, because you just want the products of these solutions times the conjugate, right? So 13 minus e to the 2k plus 1 pi over 10 multiplied by 13 minus the associated conjugate solution. So we're going to have some kind of solution, some summation for the solution. So let's look at first a brief aside. What happens when you take a complex number, 13 minus it, multiplied by its associate conjugate. Okay. Now, this just expands out into 13 minus theta plus, which this just combines into this. Now, this part, either the I theta plus e to the negative I theta, the imaginary parts cancel out and the real part is doubled. So that times 2 gives us a factor of 26. Our real part is cosine theta. Now, what does this mean? If we actually consider our solution, what do we really want? It's that summation, and we're finally ready to build it. So our summation, based on what we just did here, 2j plus 1 times pi, all divided by 10. Great. So we want the sum because basically this is we have a solution. We have solutions of the form 1 over x. Over here, what happens when we multiply them with their conjugate, um, which is what one of these terms is, we get this. And now we just sum this product for all these 5 terms, j equals 0 to j equals 4, and we get this summation. So pulling out the 170 minus 5, we get this sum. Okay, that's gonna get cut off. So let me pull it down here. Minus 26 equals 0 to 4 of cosine 2j plus 1 pi divided by 10. Okay, now the first part obviously just multiplies up to 850, right? But now let's take a look at the summation. Consider what happens when you plug in j equals 0 and j equals 4 in here. You get cosine pi over 10 for j equals 0 and cosine of 9 pi over 10 for j equals 4. Now, we quickly realize that cosine pi over 10 and cosine 9 pi over 10 are the opposite of each other. One is a negative of the other because of basic unit circle properties. So actually in our summation, these terms will cancel out with each other. And similarly, j equals 1 and j equals 3, those terms will also cancel out with each other to produce 0. So the only term that doesn't cancel out is j equals 2, which gives us cosine of 5 pi over 10. But cosine of 5 pi over 10, which is cosine pi over 2, is just 0 as well. So in fact, this whole summation just reduces to 0. And our final answer is 850. Now, if any of you had any trouble understanding the complex numbers manipulations that I did, I suggest checking out AOP's page on complex numbers. You can read up on them, find out some useful properties, which can be helpful in several problems like this one.